that go for everyone? What SHA corresponds to the commit?
I got a B160 CEF.
Okay. Anybody else get that? So you do a git, add, right? Do a git commit or just a GC alias. There's your file. So I got 7BF33F0. Anybody else get that? I'd be surprised if you did. So why is the commit SHA different even though we're all committing the same file? Any ideas? We haven't covered this yet, by the way.
Is it because different file names and or different messages in the commit message?
Okay. Yeah, that could definitely be it.
It includes your username, just in case multiple people are committing. Same
Right.
file, I guess.
Right. Yep. That's all on the right track. So recall that the hashes content, and our commit has, each of our commits will have different content, almost certainly, whether it's the file name or the commit comment, or even the commit also has a timestamp, as we'll see. So the odds of a timestamp being the same for any of us is going to be minute as well. So yeah, it would be very surprising if we got the same commit SHA, even if we had the same content for the file that we're committing. So you find the SHA under Git objects. Basically, just look for the .git /objects, and then the first two characters of whatever commit you got. Should show you the, let's see, mine was 7, so I should have an F3, F0 in there somewhere. So that should be right there. Okay. So we can use git cat file to kind of pick apart this commit. So let's see, how's the best way to go about this? Let me give you a magic command to put you back where, if you did do the commit, let's get back to where you were, so we'll all be on the same page with the rest of this handout. So do a git reset --hard head caret. I will explain that later, but for now, just do that. And you should get some output like this. Okay, so now what we're going to do is trace from head kind of down to the underlying SHA, and then we're going to pick apart that SHA and see what it's made up of. And this will get at the essence of these three objects that I've been going on about, but not really explaining thus far. So let's look and see what head is. First of all, we can go see where it is. Go into .git. And you'll notice, among others, there's a file called head. And if we see what kind of file that is, Look at that, it's not a VAX executable, it's ASCII text. So that means we can cat it. And this is literally the contents of head. So the implications is that it's a symbolic reference. So it references the master branch. So in normal Git context, you would have head pointing to symbolically to a branch, not to an actual SHA. You can make it point to a SHA. We'll cover that at some point, but normally it would just point to a branch. So
So if you checked out a different branch, like let's say branch A, it would say refs heads branch A.
yeah,
Okay.
yeah, you could git checkout or git branch. Actually, how's it go? Git checkout dash B some branch, right? Now we switch to new branch, and now we cat. Yeah, so now it's some branch.
Okay, thanks.
And then we've got a handy alias for going back to master. Now we're back on master. So let's go down and look a little bit more here. So this refs heads, that's not just it's not only a symbolic reference, it's a symbolic reference to a path. So again, there it is. So we can see what kind of file it is. I've got a pretty good idea what it is. Yep, ASCII text. And now we've got an actual SHA, right? And you may recognize that from our previous ADOG commands, is that's the SHA that head is pointing to. All right, this FC223DF. Hit Q to get out of that. You may also notice that I've used BangDollar a couple times. So you can see what that does. Basically pops in the last argument of the previous command. So it's another bashism. Bang refers to the previous command, or if you give it a number, it refers to a numbered command in your history. And BangDollar says, just give me the last argument of that command, which is often handy because you want to do several things to the same file. You know, run file on it, run cat on it, et cetera, et cetera. So that's a little shortcut, little bash shortcut for you. Yeah, so there's other stuff in this ADOG, like OriginMaster. So there's refs. Under refs, there is this remotes. And so there's a head for that as well. I can do BangDollar/head. So there's that OriginMaster. And Git just uses that to display this graph again, right? It's really, you know, not rocket science. It's all under the hood. It's just files and a cloud of these commands that Git has to pull this data model together and show you things that help you. And then if we go ahead and cat this guy, where am I at? Oh, not master head. Wait, what? What did I just do? Yes, well, OriginMaster. Lost my place here. Refs, origin. Oh, it might be under packed refs. So Git does some optimizing on these files as well as the database. So let me back out of that because I'm not quite sure how to unpack the packed refs at the moment. Sure, there's a command for that. But suffice it to say that these entities that you see up here in the ADOG command live down in the Git directory and eventually resolve to SHAs. And that's what Git uses to draw this graph. So, right. So now let's unpack the head, see what it amounts to. Go back up one. So now we're back in our repo. So you can, when you give a SHA or commit reference, you can give several kinds. You can give the symbolic reference like head, or you can give the actual SHA. You could give, you know, master might work. Nope, actually that doesn't work. Actually, cat file does need an actual SHA, never mind. No, it needs me to remember my command line is what it needs. -T. Yeah, so you can give SHA or branch or head, and it will figure out what SHA you need. So this tells us what kind of a SHA it is. And recall the -P tells us what's in the SHA. So now we're starting to get down to the tree, or get down to the relationships between these objects. So we said before that our SHAs are different when we did our different commits, and this is why they're different. It's because, you know, your tree and parent might be the same, but the author is definitely different, and the timestamp is definitely going to be different, and the committer and timestamp is also definitely going to be different. All that together, and then down here is your comment. So these are the different, data fields, if you will, of your commit SHA. So that's what a commit SHA has. You know, the parent is the thing that, you know, it points to the previous entry in that ADOG tree. You know, that's how history is built. Is your parent commit. The tree we haven't covered yet. That's the second kind of SHA, of object. So commit is the first kind. Let's look at the tree now. Give it the first few characters. Okay. So here's the second kind. Here's what a tree consists of. So this tree apparently has a blob, which we'll cover in a moment. You can have another tree, so it can be recursive. You know, you can have trees of trees of trees, just like a directory hierarchy has. And then you break down the kind of the different pieces of each one of these. There's that set of permissions, which looks a little bit like Unix permissions and is very similar but not identical. But it's enough for Git to be able to put it out into a Linux directory for you. There's the type, there's the actual where it is in Git, and then there's the file name that's attached to that tree, or a blob, in this case a blob. And so now let's go down to the very leaf node, which is a blob. Git cat file that guy too. Let's choose one that we might recognize, like get aliases. Okay. So we've seen this before, right? So that is this blob right here. So a little bit of memorization. 3 kinds of objects: commit, tree, and blob. They're all SHAs. If you hear of a SHA, people will shorthand a SHA to mean commit SHA because that's what you normally work with when you're doing things with Git. You hardly ever refer to a tree SHA or a blob SHA. But technically, all of these are SHAs, right? They're all stored with the SHA algorithm in the same place. They sit beside each other. If we look at any one of these, we'll be able to find it in Git objects, just the same way as we do any other one, right? So if we look in 7.0, we should see the rest of this. Yeah, so the A7, if we look up for the tree itself, 7.2, there's our tree, right, the 2D. So all these are stored in the same way, even though they're different kinds of SHAs. And they're all used, the content hashing is done exactly the same way for all of them, whether it's a blob, a tree, or a commit. All that machinery is done the same way for all these. So then you get, as I just pulled this directly down from gitscm.com, but I think it's useful to conceptualize what's going on, right? If we sort of move this over here a little bit. If we consider this last thing in our ADOG here to be this guy over here, we can draw something like this, right? So we've already done part of this already. We've looked at master, so this tree part would be this guy here. All these blobs and trees down here would be the contents of the tree. There's a parent, which would point back to the second commit. So this parent here, the 3E37. We look here where we're at. So here's 3E37, but just before head here, and so on and so forth. Any questions about what we've covered so far? Making sense? Basically, thumbs up, thumbs down.
I kind of have a question that probably goes a little beyond what you're doing at the moment. I was just kind of curious. I learned about this a long time ago, or I was trying to solve a problem of my own, and I didn't understand the concept at the time, but I know it now. Get all these hashes that are happening that you're looking at when you look at a tree.
Sure.
I'm assuming it's using a Merkle tree.
A Merkle tree.
Yeah, is that what's happening? Like it's like Git is basically hashing each file, and then when you look at like a tree, the tree is basically the composition of every single file's hash, all of the hashes of every file as a hash, like that tree, right?
Yeah, these are the whole tree is addresses, right? I mean, there's a BAK showing up here, but it's actually a blob hash, right? Like this.
Yeah. So what I'm saying is if I knew what hashing algorithm they use, right, and I took every single one of like Git ignores hash, readme's hash, every hash that's in here, if I ran them through the same hash functions, would I come out with the hash for this tree?
Yes.
Yeah.
Yeah, if you hash get ignore, you'll come up with this.
Oh, no. I mean, if I hashed all of them together, the tree for this has a hash too, right? So like,
Yeah, so the tree, if you hashed all of this,
yeah,
modulo of white space, right? Formatting
yeah,
nuances, you would get this tree hash here.
yeah, yeah. That's what,
Exactly.
and that's basically a Merkle tree, right? Like you're hashing all the sub elements, which equals like the. So if the hash of like the A directory that you have right there, that's where it says tree 63EF, the A directory hash.
Yeah.
It's a directory. It contains more files. That hash is basically a composition of all the files hashes inside of there.
It's a hash of whatever that tree contains. I mean,
Yeah,
there's nothing any more complicated here than this number or this SHA.
yeah,
But
yeah.
that SHA has already been wired up, so to speak, by a previous commit.
Yeah. So the reason I was learning about this a while ago was I was trying to figure out a way to like watch like figure out when the most optimized way to watch a directory for changes.
Mm-hmm.
And it made me think about hashing. It made me think a way like you can give a unique hash to every file, and then all the subdirectories within a folder, because you don't want to you don't want to you don't want to use Python to iterate over every single folder every time you detect a save, iterate over every single file, and then like parse the file and look for a change or something like that. Like you just want to like hash the hash changes of a file if you change however many bytes are in it, right? Like if you add one character, the whole hash changes. So with that, you can like combine all of that together to like watch an entire folder for one single character change of any file in that folder. And that's why I was exploring this. I was wondering, like, Git's probably doing a Merkle tree of hashes, a tree of hashes, basically the same concept. So
Yeah.
I'm just relating the thing that I was learning about a long time ago. So
100%. That's it's hashes all the way down.
yeah, thanks.
So,
Yeah.
until you want to unpack it and get at the content, right? But the structure is a structure of hashes, whether commit, tree, or blob. And then the last step is to go dereference that hash and get the thing that it points to. Now when I let me qualify that. When I say dereference, I don't mean that you take the hash and reconstruct the file. You can't do that. There's no way I could like look at this and apply any algorithm that would ever come up with this, even though it's a unique reference. It's a one-way hash, right? You have to actually go to that location in the file system and get the thing that it refers to. So that's important to keep that distinction in mind. But as long as it's unique, when you hash it and it comes up with the same thing, then you can do this addressing trick that Git does. Okay, good question. Any others? Let's move on then. Okay, so take another 15 minutes or so. So we did that already. We talked about this. Okay, let's introduce the concept of the tree. So now we're getting kind of into practical space. This has all been pretty theoretical, except for the actual commit SHA part. We do see those in practice. But the trees and blobs are just kind of, they do what they do. We don't worry about them for the most part. With these trees, the tree concept, we do start to get into the nitty-gritty. So so you make change. You're in your repo. Looking at stuff. You change something. Maybe something. You add another alias to get aliases. Just git remote, something like that. And now we do a git status, and okay, there's something changed. do git add, right? Just put it in there, git status. So what's all happening with that? Well, that's where the trees come in, and you know, I came from a background of Subversion and ClearCase and SCCS and RCS, and Subversion doesn't have any concept of an index, so that was confusing to me for a while. Why are we adding this extra step? You know, instead of just doing Subversion commit, right? But I'm getting comfortable with it. I'm not sure I completely understand why it's necessary. I'll be honest, but understanding how it works is the key to using Git effectively. So so the three trees, and this is also another qualifier. When I say tree, I don't mean this tree necessarily. I do once, but I'm using tree in a more generic sense. So in the sense that the workspace is a tree, right? Your directory has directories underneath it, which, you know, becomes a tree. So that's one of them, is your workspace, your local file system. And then the index, which, as I just did now, I just actually put something in the index. This is another sort of intermediate tree. You don't really kind of work with it that way, but that's what it is. And that's how Git refers to it. And so the index is like a staging area for Git to put a few things in. It puts some blobs and some trees into this Git directory or the Git database before it actually wires it all up into a commit and throws it in on top of a parent. So Git it's kind of for Git's purposes. It needs it. But we can do some useful things with it too. And then finally, the other tree is the actual committed stuff, the fully committed thing that head points to is that third tree that you're working with when you're doing Git commands. So it's like it's done and dusted. It's in the database as a commit. So, you know, if you don't make any mistakes, then you don't really kind of care that much. You just kind of go forward and say, okay, I'm ready to commit. And then everything just kind of works, and then you do a Git status, and now you're able to make the next change, right? This is all about what happens if it doesn't quite work right. So maybe I say, gee, you know, I didn't actually mean to say that with my commit. So you can do, you know, do an amend, right? And then give it another comment, you know, this, right? And then that works. But what really happened? You know, that's the -- amend option is really kind of a wrapper around some other stuff that goes on. Maybe you want to change the actual text of the file, right? And just kind of uncommit it. Anybody ever had that desire? Like, let me fix this up a little better.
Where you have to commit and uncommit.
Yeah, well, this is what this is. This is an uncommit that we're going to be learning how to do from a point of knowledge, and not just a magic spell that we've gotten from the interwebs. So what's going on is these trees. So head is, if you think of head, that's kind of the most what's the word? It's the direction we're going. You know, index is the intermediate spot. Your workspace is the just beginning to do, you know, put your creativity into text and code. So that's why. So the command we're going to look at to do all these manipulations is git reset. So the first thing to understand about git reset is that you're choosing some commit somewhere to lock your lock your state to, or to revert your state to. So, like when I said before, yeah, I've got my goofy commit up here. I said, let's revert this, right? And so what I did was I said git reset -- hard this. Anybody recognize what that does? Or care to try to describe what that does?
Is that the parent?
Okay.
Like the parent of head?
Yeah, this is the parent of head. That's what that syntax says. I could have said this. Whoops, not that. This. What does that say?
Oh, is that basically going up to?
Yeah, the grandparent of head, right? And I think there's even syntax that you can do something like that. I don't have it quite right, but there's a whole revision syntax that you can use in this context to say which SHA you want to point at. This is easy. You could give it a SHA. You could just say, I want to go down to here, all right? And I could give it that one, and then it would just take all my workspace index and head pointer and just put it all there, and everything would be here on this SHA that I give it. So but the important thing is you've got to give it a destination that you're going to reset to. That's a key to it. So I did that, and I've chose my place on head, or my place that I wanted head to be, and then everything, head, index, and directory all went to that place. That's what hard means. Like, just do it. And so that operates basically, with respect to your workspace, to digress a little bit, what if I have untracked changes in my workspace? Well, those are still there because they're not tracked. This only deals with things that Git actually knows about. Or that would, if Git knows about something that would conflict with what you've got already, it'll say, no, I can't do this. You got to resolve this conflict first. But otherwise, it will go ahead and make all those changes back to that place that you specify with that last argument to reset. So let's work with this a little bit. It's very useful when you know what's going on, because, and let's get back to like here, right? I could even say, well, first let me back up. So this 83C6499, what happened to that when I moved away from it? Because if I go here, it's not anywhere in my graph anymore. So what do you think happened to that commit SHA?
Did it just get moved to the Git objects directory?
Okay. You think this will work if I do this? It does work. Yeah, is it in the Git objects directory? Let's see. So it should be 8.3, right? C6499. Yep, there it is. So yeah, it is there still. It didn't actually get moved there. It was actually put there when I did the commit, right? Just like every other commit does. The takeaway here is that it didn't get taken away from the Git objects directory. It's still there, right? It's still living there. It's just not referenced by anything, but it's still there. So I could actually just say, you know what? I changed my mind. I want to go back. And now I've just gone back, right? I've just reintroduced that commit because it's still there. I haven't had to do a recommit. I didn't have to, you know, make my changes again. I just pointed head at the thing that was already there. Does that all make sense to everyone? That kind of gets at what I was talking about with respect to Git having your back. The stuff that you did is still there. So you know, it's not gone, but you have to know how to get back to it. So let's take a break for about 10-15 minutes, and then we'll pick up and get more into this.